Welcome to StudentPal. In this Grade 12 Biotechnology lesson, we begin Chapter 10, Bioprocessing and Biomanufacturing. A useful organism, cell line or enzyme becomes a manufacturing system only when its biological activity can be controlled, measured, and reproduced at practical scale. The journey begins with strain or cell line selection and continues through medium design, inoculum preparation, sterile operation, mixing, oxygen transfer, process control, product recovery, purification, formulation and batch release. Producing a large quantity is not enough. The product must also have the correct identity, potency, purity, safety, and consistency. By the end, you will be able to label a bioreactor, compare batch, fed batch and continuous operation, explain oxygen limitation and scale up, arrange upstream and downstream steps, and build high-scoring CBSE answers that connect cell physiology to engineering and quality evidence. Our roadmap follows the product from biological source to released batch. First, we distinguish a laboratory bioprocess from reproducible biomanufacturing and relate primary and secondary metabolites to growth phase. We then examine a stirred tank bioreactor, vessel, impeller, sparger, baffles, probes, temperature system, exhaust, and aseptic ports. We connect mixing, aeration, oxygen transfer rate, cellular oxygen demand, heat removal, foam and shear. Next, we compare batch, fed batch and continuous modes and construct an inoculum train through progressively larger vessels. Sensors and feedback loops maintain temperature, pH, dissolved oxygen and other critical variables. Finally, we study scale-up trade-offs, downstream clarification, capture, purification, concentration and formulation, before using yield, productivity, quality specifications, and complete batch records to decide whether manufacturing is reliable. The central challenge is that the production system is alive. Cells consume substrate and oxygen, release heat and waste, change pH, alter broth viscosity, and may respond to stress by changing growth or product formation. The reactor must therefore deliver nutrients and gases, remove heat, and maintain suitable conditions throughout the vessel. A reading at one probe does not guarantee that every cell experiences the same microenvironment. At larger scale, mixing takes longer, and gradients become more likely. Control actions such as faster agitation may improve oxygen transfer, but increase shear, foam, heat generation, and power demand. Reliable manufacturing defines critical material attributes, process parameters, acceptable ranges, sampling plans, and final product specifications. A batch is trustworthy only when both the biological output and the controlled history of its manufacture support the claim. A bioprocess uses living cells, cellular components, or enzymes under controlled conditions to make or transform a product. Examples include microbial production of an enzyme, cultured cell production of a therapeutic protein, and enzyme-catalyzed conversion of a substrate. Biomanufacturing implements that process repeatedly at production scale. The scientific mechanism remains essential, but manufacturing adds qualified raw materials, controlled equipment, validated procedures, trained operators, in-process tests, traceable records and release specifications. The complete chain is source selection, upstream preparation, production, downstream recovery, formulation, quality testing and distribution under suitable conditions. A high titer does not excuse the wrong molecular identity or unacceptable impurity. The goal is not merely to make product once, it is to make the intended product consistently, safely, and economically across batches. Primary metabolites are closely associated with essential growth and central metabolism. Their production often rises while cells are actively growing, although the exact pattern depends on organism and conditions. Secondary metabolites perform specialized ecological roles and are frequently produced after rapid growth slows or under particular environmental signals. Antibiotic production is a familiar example, but students should avoid treating every product as following one universal curve. Plot biomass and product concentration against time and identify whether product formation is growth associated, non-growth associated, or mixed. That relationship guides nutrient feeding, oxygen supply, and harvest time. Excess substrate may inhibit cells or produce unwanted byproducts, while premature harvest sacrifices product. Process design therefore begins with a production profile measured under controlled conditions rather than a memorized assumption about growth phase. A stirred tank bioreactor is a closed vessel designed to support biological conversion. The impeller moves liquid and disperses gas. Baffles reduce simple swirling and improve mixing. A sparger introduces sterile gas as bubbles, increasing gas-liquid contact, while the exhaust system removes gases through suitable filters and may support off-gas measurement. A jacket or internal heat transfer surface adds or removes heat. Probes monitor variables such as temperature, pH, and dissolved oxygen. Ports permit sterile addition, inoculation, and sampling. Foam may be detected and controlled mechanically or with carefully managed anti-foam. Seals, valves, and connections must maintain containment and sterility. Every component has a purpose, but performance depends on the complete system. A label diagram earns marks when each label is linked to its biological or engineering function. Aerobic cells use dissolved oxygen, but oxygen has limited solubility in aqueous medium. Aeration introduces oxygen to the gas phase, and agitation renews the gas-liquid interface and distributes dissolved oxygen through the broth. The oxygen transfer rate depends on the mass transfer coefficient, interfacial area, and the difference between saturation and actual dissolved oxygen concentration. Cellular oxygen uptake rises with viable biomass and metabolic activity. If uptake exceeds transfer, dissolved oxygen falls and metabolism or product formation may change. Increasing agitation or airflow can help, but more is not automatically better. Shear-sensitive cells may be damaged, foam may increase, and power and heat loads rise. Oxygen enrichment, pressure, impeller choice or feed adjustment are other options. Diagnose limitation with dissolved oxygen, biomass, substrate, product and off-gas evidence before changing the process. In batch culture, the reactor receives its starting medium in inoculum, operates without continuous nutrient feed or product withdrawal, and is harvested at the end. Conditions change as nutrients are consumed and products accumulate. Fed batch culture adds selected nutrients during operation without removing an equivalent culture volume. It can prevent substrate inhibition, extend production, and control growth or product formation. Continuous culture introduces fresh medium while removing culture at a matching rate, allowing a controlled operating state when dilution and growth are balanced. Continuous operation can offer steady productivity but requires long-term stability and has greater exposure to contamination or genetic drift. Compare the modes by material flow, control of substrate duration, productivity, operational complexity, and contamination risk rather than memorizing only definitions. Upstream processing includes all work that prepares the biological system for production. A suitable strain or cell line is selected for product formation, stability, growth, and safety. Cell banks preserve characterized starting material and reduce uncontrolled drift. Medium development balances biological performance, raw material consistency, cost, and downstream consequences. Equipment, gas, and medium are sterilized or otherwise controlled using validated methods appropriate to the process. The inoculum must have the correct identity, purity, viability, physiological state, and volume. Operating ranges for temperature, pH, oxygen, agitation, feeding, and harvest are established. Weak inoculum quality can create a long lug phase, altered metabolism, or failed production, even when the main reactor settings look correct. Upstream acceptance criteria turn preparation from an informal sequence into a controlled manufacturing stage. An inoculum train expands a small characterized culture into enough healthy biomass to start the production reactor. A vial from a qualified cell bank is revived and transferred through a starter culture and progressively larger seed vessels. Each stage uses a defined transfer ratio and physiological window so cells do not enter the next vessel stressed, nutrient-depleted, or contaminated. Acceptance checks can include identity, morphology, viable count, growth rate, and absence of contamination. The scale steps must preserve the intended phenotype and product forming capacity. Simply transferring by clock time is unreliable if growth differs between batches. Records connect every production run to the originating vial, operator, medium lot, vessel, conditions, sampling results, and transfer decision. The inoculum train is therefore both a biological expansion and a traceability chain. Online sensors provide frequent measurements of temperature, pH, dissolved oxygen, pressure, agitation, and airflow. Other values, such as biomass, substrate, byproducts and product, may require aseptic sampling or specialized online methods. A feedback controller compares a measured value with its set point and changes an actuator. For example, falling dissolved oxygen may trigger a cascade through agitation, airflow, or oxygen enrichment. pH can be adjusted through acid, base, gas composition, or feed, depending on the system. A control loop is only as reliable as its calibrated sensor, correctly placed probe, suitable sampling frequency, and validated actuator response. Process control should not hide biological change. If oxygen demand suddenly rises or pH correction becomes excessive, investigate cell physiology, contamination, feed and probe performance rather than treating the display alone. Suppose dissolved oxygen falls while biomass is rising. One interpretation is that cellular oxygen uptake has increased beyond the current transfer capacity. Before accepting it, confirm probe calibration and examine agitation, airflow, pressure, foam, substrate and off-gas trends. If the signal is real, the control system may increase agitation and aeration within validated limits. Recovery of dissolved oxygen is an engineering response, but product formation, viability and byproduct levels reveal whether the biological system remains healthy. If oxygen drops despite maximum control action, feed may need adjustment or the process may have exceeded its transferable operating range. In an exam data question, describe the observation first, propose a mechanism, name corroborating measurements, state a control action, and identify the trade-off, such as increased shear or heat. Scale-up is not simple geometric enlargement. When vessel volume increases, distances grow, surface area to volume relationships change, and mixing can take longer. Cells may experience temporary gradients of substrate, oxygen, pH, and temperature. Heat generated by metabolism and agitation becomes harder to remove, while gas dispersion and foam behavior change. Maintaining the same agitation speed does not preserve the same impeller tip speed, power per volume, or oxygen transfer capacity. No single rule keeps every parameter identical. The scale-up criterion must match the process limitation: oxygen transfer, mixing time, shear sensitivity, heat removal, or another critical factor. Pilot-scale studies, scale-down models, and process data reveal risk before full production. Successful scale-up preserves product quality and cell performance within acceptable ranges, not visual similarity between vessels. Downstream processing begins when the product must be separated from the culture. For an extracellular product, cells and debris are removed while the product remains in the liquid. An intracellular product requires controlled cell disruption followed by removal of insoluble material. Capture steps rapidly concentrate and isolate the target from the bulk mixture. Intermediate and polishing purification remove progressively more difficult impurities. Concentration and buffer exchange prepare the product for formulation, filling, and storage. The sequence depends on product location, size, charge, binding behavior, stability, required purity, and cost. Every transfer risks loss or damage, so gentle conditions and stage-wise measurements matter. A beautifully pure final sample can still represent a poor process if recovery is extremely low or function has been destroyed. Quantitative process evaluation separates concentration, total amount, yield, and productivity. Suppose the clarified feed contains 120 grams of target product and purification recovers 90 grams. Stage recovery is 90 divided by 120 times 100, or 75%. This calculation needs total product amount, not concentration alone, because process volume may change. Overall recovery is affected by every downstream step and is usually lower than the recovery of any single successful stage. Volumetric productivity reports product made per reactor volume per unit time, allowing fairer comparison between processes of different size or duration. Titer describes product concentration at harvest. A process can show high titer but weak productivity if it takes very long, or high recovery but inadequate purity. Always state the metric, units, denominator, and quality context. Manufacturing quality is designed into the process and confirmed by testing. Critical material attributes describe inputs that can affect performance. Critical process parameters are operating variables whose variation may change product quality. In-process controls reveal whether the run remains within its validated state. Final specifications can include identity, potency, purity, concentration, sterility or microbial limits, endotoxin where relevant, and stability. Acceptance criteria are defined before results are seen. Deviations require documented assessment rather than silent adjustment. Batch records preserve raw material lots, equipment status, calibration, operator actions, process trends, sampling and results. Environmental monitoring, containment and waste treatment protect workers and surroundings. Consistency does not mean every numerical value is identical. It means controlled variation remains within justified ranges and each released batch is suitable for its intended use. For a CBSE answer, define a bioprocess and distinguish biomanufacturing by scale, reproducibility and quality controls. In a stir tank diagram, label impeller, baffle, sparger, probes, temperature system, ports and exhaust, then state each function. Explain oxygen limitation as cellular demand exceeding transfer and discuss aeration, agitation, bubble dispersion, viscosity, shear and measurement. Compare batch, fed batch and continuous modes in a parallel table using material flow, substrate control, duration, productivity, complexity, and contamination risk. Write upstream processing from cell bank and medium through inoculum and sterilization. Write downstream processing from clarification or disruption through capture, purification, formulation, and storage. In calculations, show formula, substitution, units, and interpretation. End with identity, potency, purity, safety, stability, and complete records. Close your notes and rebuild the chapter. Bioprocessing uses cells, components, or enzymes for controlled conversion. Biomanufacturing makes the process reproducible at production scale. Product timing can follow growth or specific later physiological conditions. A bioreactor integrates mixing, aeration, heat transfer, sterility, sensing, and sampling. Oxygen transfer must meet demand without unacceptable shear, foam, or heat. Batch begins with a fixed charge. Fed batch adds selected nutrients and continuous operation balances feed and output. Upstream work establishes the production source, medium, sterile equipment, inoculum and operating conditions. Sensors and feedback loops control defined variables, but biological data must confirm the response. Scale-up changes mixing, gradients, oxygen and heat. Downstream steps clarify, capture, purify, concentrate and formulate. Recovery and productivity need correct denominators. Identity, potency, purity, safety, stability, and traceable records support consistent batch release.